and welcome to this lecture. In this lecture, we're going to study what's called the discrete Fourier transform. So this has very, very important applications in signals, filter design, etc., etc., etc. I don't have to tell you, but the crux of this definition is the connection with circulant matrices and Fourier bases that we saw earlier. Okay, so it's a very interesting application of linear algebra. So let's see it. So for that, we need to first define something called a DFT matrix. Once again, omega is e power I 2 pi by n, and u0 to un minus 1 is my Fourier basis. What do I know about the Fourier basis? It's orthonormal, right? So Fourier basis is orthonormal. So when I have an orthonormal set of vectors, I can make them into a matrix like this: u0, u1. Each column is a vector, and we know that this is a unitary matrix, right? So because any two columns are perpendicular to each other, and the norm is 1. Let's write each vector out in full detail. The first vector is all ones. The second vector is 1 omega omega square omega power n minus 1, right? The second column, which is u1. The third column is u2, and that is 1 omega squared squared, so on till omega power n minus 1 squared. The last column is un minus 1, and that is 1 omega power n minus 1 omega squared power n minus 1, so on till omega power n minus 1 into n minus 1. Okay, so that's the one matrix for you. This is the matrix where every Fourier basis vector went into the column. Okay. Now you can also consider the Hermitian of this guy. Okay. So remember, this is a Fourier basis, so it's orthonormal. So when you have a unitary matrix, it has a connection with its Hermitian transpose, right? So you do the Hermitian of this. You're going to get u0 Hermitian, u1 Hermitian, so on till un minus 1 Hermitian. So every column I have to take Hermitian, and I have to write it as a row vector. So this whole thing will become, this first row is 1, so first column will become 1. So likewise, you have to see how to do this. So let's go row wise here. The first row is 1, so the first column becomes 1. The second row is 1 omega squared till omega power n minus 1, so the first column will become 1 omega inverse omega power minus 2, say omega power minus n minus 1. The third row is 1 omega squared till omega squared power n minus 1. So down here we'll have 1 omega power minus 2 squared till omega power minus n minus 1 squared. So you see how the plus and the minuses are working here. Okay, so here you have positive powers. All you have to do is just make minus. Wherever you have omega, put a minus 1 instead of the plus power that it has, you get the Hermitian. Okay, so notice the patterns here. The patterns here are all very intriguing patterns. The way these rows and columns come, this is very important. So these matrices are well studied in signal processing. Okay, so this is the Fourier basis with each basis vector coming in the column. Here, every row is actually the Hermitian conjugate of this u0, u1, etc. Okay, so that's the thing. Okay, so the second matrix here is actually defined as the DFT matrix typically. Okay, so this is the n by n DFT matrix. It's denoted DFTn. I will denote it DFTn in this lecture. A lot of signal processing people will not use this 1 by root n. They'll define DFT without the 1 by root n. That causes a lot of scale adjustment, but I'm going to define it as 1 by root n. Okay, so this is my DFT matrix. So this is actually this DFT matrix Hermitian, isn't it? So if you define this as the DFT matrix, the Hermitian is that. Okay, other way around. Okay, so this is how the DFT matrix is typically defined. You can also, of course, define the DFT matrix with this. Everything is equivalent, but this is the common terminology. Okay, so this is clearly a unitary matrix. You can check this out. DFTn Hermitian is the same as DFTn Hermitian, DFTn, and this is just I. Okay, so that's an important fact to remember. Okay, so this is DFT matrix. It's a unitary matrix. Okay. So what's the nice fact about DFT matrix? So for that, let's try and look at the circulant matrix again. So we'll go back to the circulant matrix, and we already know that for this circulant matrix, and now I'm generalizing the circulant matrix. So you see the first column is h0 h1 to hn minus 1. The second column is a circular shift and so on. Okay, the same with the rows also, we know this. Instead of starting at h7 or something, stopping at h7, we are going on and on for a general n here. Okay, what is the kth eigenvector here? It's uk 1 by root n. This is the standard Fourier basis. Now let's start thinking about the eigenvalue associated with this eigenvector. So I'm going to call the eigenvalue as lambda k. So if the eigenvalue is lambda k, muk is lambda k uk, right? So this is an eigenvalue. So if I take this m, multiply with uk on the right, I'm going to get some constant into uk. That constant is going to be some complex number. That is my eigenvalue. Right? That's what makes it an eigenvector, isn't it? So now let's try and find out what this lambda k is. Okay, it's easy to find out lambda k from this equation, right? So, it's easy to do that. So, let us just say m times uk is t0 till tn, okay, some t0 to tn. If I multiply with uk on the right, I am going to get t0 to t. Now, t0 is very easy to write down, no? So, t0 is actually 1 by root n times the first row, right, h0, hn minus 1 till h1 multiplied by this column, isn't it? This column vector here. Is that okay? Hopefully, you are seeing this. The t0, the first entry of muk is just the first row here multiplied by this guy. So, of course, 1 by root n will come here, the first row multiplied by this guy, okay. How do you simplify that? Okay, you may simplify it, but it does not matter how you simplify, it has to become 1 by root n lambda k, right, according to this equation. So, muk is lambda k into uk. Lambda k into uk is just 1 by root n into lambda k. So, whatever you get as muk, which is t0, has to be equal to this. So, this will directly tell you what lambda k is, okay. So, sort of a easy way, given the eigenvector, finding the eigenvalue is very easy, okay. So, this is the idea behind it, okay. So, now let us simplify this guy. So, lambda k, of course, 1 by root n will cancel. So, lambda k is h0 into 1 plus, let me start with h1, okay, maybe it is hn minus 1, hn minus 1 into omega power k, hn minus 2 into omega power 2k, so on till h2 into omega power n minus 2 into k, h1 into omega power n minus 1 into k, okay. Let us change this around a little bit, it is h0 plus h1 into omega power minus k, do you agree? Right, omega power n minus 1 into k is the same as omega power minus k, right. So, omega power nk minus omega power nk minus k, right. What is omega power nk? That is just 1. So, omega power minus k alone will remain, okay. So, convince yourself that this is true, okay. So, omega power n minus 1 is the same as omega power minus 1. So, that whole thing raised to the power k is omega power k, okay. Same thing here, omega power n minus 2 into k is omega power minus 2k, so on, so forth. At the same way, hn minus 1 omega power k I will write as omega power minus n minus 1 into k, okay. All of these are written in terms of this minus, so that you get this very nice looking equation here, h0 plus h1 omega power minus k, h2 omega power minus 2k, so on till hn minus 2 omega power minus n minus 2k. Whatever coefficient of h you are getting, hn minus 2, you simply do omega power minus n minus 2 into k, okay. So, this nice looking expression is my lambda k, okay. You can also check, if you have time, that the other guys, the TL will actually be 1 by root n lambda k omega power L with this kind of a substitution, okay. So, you can check this, I am not going to do it, I will leave it as an exercise, it is an important exercise, please make sure you do it, you will get a good handle on how these things work. So, the eigenvalues of a circulant matrix are given by this expression, and it's nice to see, right. So, h0 to hn minus 1, whatever n may be, whatever the h's may be, the eigenvalues are given like this, as long as the matrix is circulant, okay. So, this is a very nice structural result. So, if you see, if you have a 1000 by 1000 matrix, finding the eigenvalues is a little bit hard, isn't it? So, you don't know what the eigenvalues are, but if the matrix is circulant, you can write down the eigenvalues or expression for the eigenvalues very, very nicely. So, okay, so that's the power of this result, it's quite a powerful one, okay. So, from this we get a definition for what's called a n-point discrete Fourier transform of a sequence, okay. So, the Fourier base is u0 to un minus 1, the n-point DFT of a length n vector h, okay. So, we will start with, okay, so what is the discrete Fourier transform? Its input is a length n vector small h, its output is also a length n vector, okay. So, this is the definition here. So, the n-point DFT has input which is a length n vector, usually it is called with small letters h equals h0 to hn minus 1. The output is also a length n vector. What is the length n vector? I will call it capital H here, h0 to hn minus 1, and the output is nothing but, okay, the kth coordinate of the output, all these are complex numbers, okay, h0 to small hn minus 1 complex numbers, capital H0 to capital Hn minus 1 again all complex numbers, capital Hk, the kth coordinate is nothing but the inner product of small h with uk, okay. Alright, the unitary, the Fourier base is uk, you do an inner product of h with uk. Now, what is inner product of h with uk? uk is this guy, right. So, let us just see what uk is. Uk is this vector. If you do an inner product of h with uk, you're going to get something that looks like this, no? Right, because UK, I'll have to do Hermitian for it. If I do Hermitian, it will become 1 omega power minus k, omega power minus so on. So, you multiply this and you get this. So, let me just maybe write that down for you explicitly. UK is 1 by root n, 1 omega power k, omega power 2k, so on till omega power n minus 1 into k. So, if you do UK Hermitian, you are going to get 1 by root n, 1 omega power minus k, omega power minus 2k, so on till omega power minus n minus 1 into k. So, if you do inner product h with UK, it is the same as this Hermitian multiplying h is nothing but h0, h1 to hn minus 1, right. So, when you do inner product, you are going to get 1 by root n into h0, right. My inner product of this and this, h0, h1 omega power minus k plus h2 omega power minus 2k plus so on till hn minus 1 omega power minus n minus 1 into k. Okay. I hope this inner product definition is clear, and you see that this inner product works out to be like the eigenvalue, isn't it? So, this is nothing but the lambda k, isn't it, this definition. So, the DFT is basically the eigenvalues. You given a circulant matrix with h0 to hn minus 1, I define the DFT of h0 to hn minus 1 as the eigenvalues, okay, which is nothing but the inner product with h comma uk. We are in a unitary world, right. So, this is just the unitary thing. So, what you see easily is that the DFT is nothing but the coordinates of the vector h in the Fourier basis, okay. So, that is what these things are, right. The Fourier basis is an orthonormal basis, okay. So, notice how much linear algebra is used in these definitions, right. So, UK is a Fourier basis vector, and it's orthogonal with everything else. So, if I have to take this vector h, okay, and express it in terms of the Fourier basis, okay. So, this h is in the canonical basis, let us say h0 to hn minus 1. How do I express it in the Fourier basis? In the Fourier basis, I have to take the inner product of h with uk, and that is just this, and that is related to the eigenvalues also, okay. The coordinates are the eigenvalues, because the Fourier basis is an orthonormal basis, okay. It is a basis of eigenvectors for my circulant matrix. So, all of these connections come in very nicely together, okay. So, now go back to this DFT n definition, which was u0 Hermitian, u1 Hermitian to un minus 1 Hermitian. So, you see nothing but capital H is DFT n into small h, this matrix DFT n times small h, which is the same as what we did before, okay. So, in signal processing, people will call the small h as being in the time domain, which is nothing but the canonical basis. Once you multiply by this, you get the same vector in the frequency domain, and that basically is expressed in terms of the Fourier basis. So, the whole DFT is just a change of basis operation. You are going from one coordinates which you call time domain, which is in the canonical basis. You apply this DFT n transform, or you take inner products with these Fourier basis vectors. You get the same vector in the frequency domain, and that is expressed in the Fourier basis, okay. So, this is the wonderful linear algebra connection to Fourier transforms in the discrete signal processing world. Okay, now let us look at what happens let us go back to the circulant matrix and the convolution that we had, and multiplying circulant matrix with the vector on the right to get the output as the convolution, right. Interpret it in terms of the DFT, using the DFT, using the diagonalization with the DFT. Let us write it, okay. So, we know that a circulant matrix has this orthonormal diagonalization using the DFT matrix, right. So, the eigenvalues are actually root n into hk, just watch out for that small difference. So, if we define the capital H as the Fourier transform DFT of the first column here, h0, h1 to hn minus 1, the actual eigenvalues are root n times that, okay. So, if you do DFT n Hermitian here, then the eigenvalues, the values on the diagonal will be root n times h0. That is one minor root n you have to keep track of, I think, okay. So, this is my orthonormal decomposition. So, this matrix is actually equivalent to the diagonal matrix in this basis, right, the DFT basis, okay. So, that is what this means, okay. So, now let's see how to do multiplication with x. So, supposing you have a vector x and it has a DFT capital X. So what is the meaning of DFT? What is capital X? Capital X is DFTN into X, right? Right, remember that. So that is the DFT, isn't it? So DFT is, when I say DFT X, it means DFT N matrix times X, isn't it? So that is capital X, okay, keep that in mind. So if I do M times X, it's the same as this guy multiplying X. What is DFT X into X? DFT X into X, that is nothing but this guy, right? Capital X, okay, that is the DFT capital X. So let me maybe write this down for you more clearly. Okay, and one page here. So I have my circulant matrix being DFT n Hermitian times this diagonal matrix root n h 0, root n h n minus 1, 0 here, times a matrix DFT n. Okay. Now I want to do mx, okay, but I want to use, instead of m, I want to use this guy, I want to do mx. So when I do mx, what will happen? I will get mx equals DFT n Hermitian times this, all of these guys will remain the same. I will do DFT n times x. Now this DFT times x is actually the DFT of x, which has been written as capital X, x0 to xn minus 1. Okay, so that's what this means. When I say as vector x has DFT capital X equals x0 to xn minus 1, it means DFT n into x is this vector. So instead of this vector, I can put this vector here. Okay, so if I do that, I'm going to get DFT n Hermitian times this diagonal matrix, zero, 0 here, and then capital X0 to capital Xn minus 1. Now what will happen when a diagonal matrix multiplies a column vector here? I'm going to simply get DFT n Hermitian, this mx, which is a vector, times these two guys. These two guys, if you multiply, you're going to get root n h0 x0, root n h1 x1, all the way down to root n hn minus 1 xn minus 1. Hopefully you see that. This is just a diagonal matrix multiplying this, is just scales. Okay. So now this equation is very interesting, but what I can do here is I can multiply by DFT on both sides. Okay, maybe on the left, sorry. Multiply with DFT on both sides. What will happen? You will get DFT n, multiply with DFT on both sides, right? So let me say x and all that. Multiply with this on both sides times fx mx. What will happen if DFT multiplies DFT n Hermitian? It will just go away, right? So you will just get root n h0 x0 all the way till root n hn minus 1 xn minus 1. Now, but what is this guy? DFT n multiplying mx. This is nothing but the DFT of the output mx, y equals mx. Okay. So the DFT of y is nothing but this guy. So it's just h0 x0 hn minus 1 hn minus 1. So DFT of y is DFT of h. Okay, of course there is a root n here, so keep that in mind. Root n into DFT of h, element wise product with DFT of x. Okay, so this is the big result that you have with the multiplication of in terms of the Fourier basis. In terms of the Fourier basis, instead of thinking of circulant matrix, if you do multiplying m with x, you have to do this multiplication row by row by row. But if you go to the DFT or Fourier world, the multiplication simply becomes just element wise product, just one product to do. You take the h zeros, multiply with these capital X zeros, you get the DFT of mx. So a lot of times this is the relationship here. Convolution in time domain, which is capital Mx, is the same as element wise product in frequency domain. Okay. So this is used to great effect in signal processing. You will read about this and do a lot of studies carefully with it in signals and systems and DSP and such courses. You don't have to know all the implications here, but I think you have to really know that linear algebra is at the heart of it. Okay, diagonalization, orthonormal diagonalization of a circulant matrix is at the heart of it, and the Fourier basis, orthonormality of the Fourier basis is very important to study. Okay. that, we'll conclude this module. Thank you very much.